Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss FRESNEL'S integrals. Let's begin. Fresnel basically proposed his theory named as Fresnel's half-period zones that clarify what be the intensity of light on that of screen when we obtain a diffraction pattern. Again, he introduced another method which is known as the Fresnel's integrals. With the help of these Fresnel's integrals, we can easily evaluate what be the intensity of light on that of screen when we obtain a diffraction pattern by using Fresnel's integrals concept. Let us consider a source S and there will be the screen O, the center of that of screen. Let the wavefront starting from that of point S, let us consider a spherical wavefront. We consider the spherical wavefront. Let X, Y and P be the pole of that spherical wavefront. The light ray travels in this direction, point Q, and light ray travels in this direction. At point O, we observe either maximum or minimum that can be defined what should be the path difference between these two rays. Write something here. The path difference delta between the waves traveling along SQO and SPO is given by that is delta is equal to the path difference. We just subtract that length to this length. We have SQ plus QO minus SP plus PO. Let us say the distance between SP and U and distance between P to O let V. Here if we take that be the source, then another wavefront can be drawn like this way. Another wavefront X dash, Y dash. that point q q dash. Since xy is a spherical wavefront, so sp is equal to sq, means these two are equal as the radius of that particular sphere or particular circle. In that of case, the path difference between these two will be q dash, as we shown in that of figure. Delta is equal to sq plus qo, sq plus qo, sq is equal to u plus qo. In place of qo, so draw the perpendicular from q to that line, let it is n, q dash to that line, let it is n dash. So in place of qo I can write that is q dash plus q dash o, q dash plus q dash o, that qo is equal to q dash plus q dash o minus sp, which is u, plus po, which is v, is equal to u plus q dash plus q dash o is equal to po, q dash o is equal to po again for that particular wavefront. So that distance will be v. In place of q dash o I write v minus u plus v. Therefore we have u plus q dash plus v minus u minus v, plus u minus u plus v minus v cancel out. So the path difference we obtain, that is q dash. q dash is the path difference. If we consider that source and the observational point are at large distance from that point q dash, that path difference can be denoted as delta. So as we write here, if the source S and observational point at a large distance from q dash, so it is termed as delta, a small distance. So we have the path difference delta is equal to del, very small distance. Look here that figure. So that distance q dash is very small. So in place of q dash I can write that is np plus pn dash. It is just seems like that of a rectangle. q dash is written as np plus pn dash. Now delta is written as or delta is equal to np plus pn dash. Now we use the geometry of circle. Use the geometry of circle. Geometry of circle, and this one is assumed as a circle. XY is a part of circle. So Qn from S, Sn is perpendicular to that of Qn. According to that of geometry, the value of Pn is equal to the square of nq divided by 2 times of that radius Sp. From the circle of geometry, we obtain Np is equal to nq square divided by 2 Sp. Similarly, again here in place of Pn dash, we obtain that is n dash q dash square divided by Po, at that of particular wavefront x dash y dash we have Po as the radius. We obtain Pn dash is equal to n dash q dash square divided by 2 Po. Now the values are put here. We write the path difference delta is equal to n q square divided by 2 Sp plus n dash q dash square divided by 2 Po. Let we take its corresponding values. Nq, let we say nq and n dash q, let y. For large value of u, that the distance of that of pole of the wavefront to that of source, and v, that is the distance of the object, the distance, the point of observation to that of pole of the wavefront, that is v. At that of case nq is equal to n dash q dash, let we say that value will be y say. Now putting the values in place of nq, you have y square divided by 2 u Sp u, next n dash q dash square y square divided by 2 in place of Po, that is v. Solving it, delta is equal to, taking y square by 2 as common, 1 by u plus 1 by v, or delta is equal to y square by 2 as common, taking LCM uv, v plus u divided by uv, or delta is equal to y square by 2 u plus v divided by uv. That is the path difference. Now the phase difference let phi, which is equal to 2 pi by lambda into path difference, relation between phase difference and path difference, or phi is equal to 2 pi by lambda into path difference y square by 2 u plus v divided by uv, or phi is equal to 2 to cancel out, pi by lambda y square by uv of u plus v, the phase difference, this is the path difference, that one with the phase difference. Equation number I and equation number double I. To achieve the FRESNEL'S integrals, here FRESNEL'S integrals are the integrals having x and y coordinates. The change in coordinates are given by dx, change in x coordinate, dr cos phi, change in y coordinates, dy is equal to dr sin phi. Phi, as you know, the phase difference. On integrating above equations, we have x is equal to integration of dx, which is equal to integration of cos phi dr from 0 to r, and y is equal to integration over dy, which is equal to cos sin phi dr integrating from 0 to r. These two equation number 1 and equation number 2, these two are known as FRESNEL'S integrals. These two integrals are known as FRESNEL'S integrals. Now, by using the FRESNEL'S integrals, we can draw the figure of the intensity distribution as x o x dash, y O y dash. For first equation, we have the figure just like this. See the figure for intensity distribution, and for y we have the figure this figure is known as the CORNU'S spiral. That figure is known as the CORNU'S spiral. By using the FRESNEL'S integrals, we have the CORNU'S spiral. CORNU'S spiral is nothing, that is the plot of FRESNEL'S integral. CORNU'S spiral is the plot of FRESNEL'S integral. Let me take a point here. Which is at a distance of r, and it has a phase angle phi at that point M. So, from the concept of that CORNU'S spiral, the phase lag phi at any point on that of wave front represented by the phase phi is directly proportional to the square of distance of r. That measured along spiral curve. Along spiral's curve, means phi is directly proportional to r square. Let equation number 3. Or phi is equal to, using a constant, pi by 2 r square. That is equation number 3. Now we compare that equation with equation number 2. Here phi is equal to pi by lambda, that much. Here phi is equal to pi by 2 r square. Comparing equation 2 and 3, equation 2 and 3, we have pi by 2 r square is equal to pi by lambda y square by u v of u plus v. Pi cancel out, or r square is equal to 2y square divided by u v lambda u plus v, or r is equal to, taking its under root, we have under root of y square, that is y, 2 u plus v divided by u v lambda under root. Knowing the values of u, v, y and lambda, we can analyze the diffraction pattern by using that CORNU'S spiral. So we write, knowing it, the values of u, v, y and lambda, we can analyze any diffraction pattern by using CORNU'S spiral. CORNU'S spiral. Knowing these values, we analyze different type of diffraction pattern. So here we obtain two integrals having the result from CORNU'S spiral. So the value of pi can also be substituted here. Therefore, putting the values of phi, we have x is equal to integration over dx from 0 to r cos pi r square by 2 dr, and y is equal to integration over dy integration from 0 to r sin pi r square by 2 dr. These two are the FRESNEL'S integrals. FRESNEL'S integrals as we know it. FRESNEL'S integrals. From the value of x and y, we can easily calculate the intensity, as these two represent the resultant amplitude in terms of x and y. Therefore, resultant amplitude, resultant intensity I is equal to k x square plus y square. X and y are the x component and y component of the resultant amplitudes. Therefore, k is the proportionality constant. Therefore, we have resultant intensity can be calculated by using that formula. So, with the help of this visual lecture, we understand what are FRESNEL'S integrals. By using FRESNEL'S integrals, we can calculate the intensity of light as we obtain the diffraction pattern on the screen. The path reference, then phase reference, taking the coordinates axis, these integrals are termed as FRESNEL'S integrals, and draw the CORNU'S spiral. These two are named as the FRESNEL'S integrals. Then resultant intensity can be calculated by using that formula. So, with this useful and informative notes, let me wind up this session. Thank you.